Hello everyone, I'm Ningning. Today I'm going to present Staging with Class, a specification of typed template Haskell. Multi-stage programming is an established technique for generating efficient code with predictable performance. Essentially, while a normal program takes some input and produces some output, multi-staging program divides compilation into multiple stages. In each stage, the program is given some input of that specific stage and is partially evaluated according to the input to generate efficient code for later stages. The Hello World example of multi-staging is the power function, where we would like to calculate n to k. The power function pattern matches on k. If k is 0, the function returns 1, or otherwise it recursively calls itself with k minus 1. We can also define a function power 5 that fixes the exponent to 5. In this case, since 5 is fixed statically, we can consider 5 is provided at an earlier stage than n, and we can use multi-stage to generate efficient code for power 5. Specifically, we distinguish between int and code int, where code int is information available in later stages. We use the bracket operation to code an int into code int, and we use the dollar operation to splice code int into int. With multi-stage programming, we can generate the definition of power 5, where the function call and all required multiplications have been unrolled and inlined. That is, we successfully eliminate the abstract overhead in power 5. In this example, we restrict the second argument of power to be an integer. But the power works for any real numbers. As a proud Haskell programmer, I can generalize the type of this function to take a type class constraint number a, so that this function can be applied to any instance of number. We would expect that this program continues to work. It is somewhat surprising then that this function actually fails to compile in the latest implementation of the template Haskell in GHC9. The error message is also mysterious. The compiler complains that it cannot find an instance for number a, while we have this instance right there in the program. So what is going on here? The problem reveals itself after dictionary parsing elaboration, which gives semantics to type classes. After elaboration, a type class constraint corresponds to an extra parameter for the corresponding dictionary, and the dictionary is explicitly passed around to satisfy type class constraints. Now we can observe the problem. In QPower, the dictionary is bound outside of the quotation and is used inside. Similarly, in Power 5, the dictionary is defined outside of a splice and is used inside. This kind of use of variables is considered ill-staged in multi-stage programming. Intuitively speaking, it means that the variable is defined in some stage and then is used in a different stage. In this paper, our proposal is to introduce staged type class constraints, a new constraint form called C, indicating that the constraint has been staged. Using staged type class constraint, we can use code C to indicate that this type class constraint number A has been staged. After elaboration, since the type class constraint becomes an extra parameter, we can model it using code. So no extra type constructor is needed after elaboration. Inside the function definitions, we use quotations and splices to adjust the dictionary to make sure it is well-typed and well-staged. In summary, inspired by the unsoundness issue in the current implementation of typed template Haskell, where splicing a well-typed code value can raise a type error, we formalize a source calculus which models type classes and multi-stage programming, and includes a novel construct, staged type class constraint that resolves the subtle interaction between the two. The source calculus then elaborates to a polymorphic lambda calculus extended with quotations, which includes a key innovation, splice environments, that gives more implementation freedom about quotations. We prove both calculi are type sound. Our work provides a solid theoretical foundation for integrating type classes into multi-stage programs. We encourage interested audience to read our paper for more details, and we thank you for your attention.